Boa tarde a todos e a todas. Estamos aqui de volta aos seminários do Grupo de Dinâmica, Orbital e Planetologia, nesse segundo semestre. E hoje a gente tem uma convidada do exterior, que está presente aqui, então ela vai fazer a apresentação aqui em loco e está sendo transmitida para todos, então a partir de agora eu vou falar em inglês, ok? So, good afternoon to everybody. And today we have the pleasure to have here with us Anna Penzlin. She got her graduation and postgraduate course in Germany, and now she's working at Imperial College in UK, in England. And she will talk about the formation, or the composition of hot Jupiters through their formation paths. So, please.
Test. Okay, that works. Yeah, thank you. So, yes, as you can already see, this is part of a very large program given the list of co-authors. And what we want to do is find a way to actually understand from the exoplanets how hot Jupiters form, and then about planet formation in general, what we can deduct. And how do we do this in this program that is mainly an observational program, and I'm just the theoretical side of these things, is it's an observational program using the James Webb Space Telescope, which has this really cool new capability to measure the atmospheres of exoplanets when the planet transits the star like this. So in usual transits that we had with Kepler or with TESS, we would just measure the dip in light that we have in a light curve, and then by this dip in light, we now roughly know what is the radius of the planet, and if it appears several times, we know what's the period of the orbit, and that there actually is a planet. But now with James Webb, what we can do in addition to that is not just measure one light curve, but we measure the light curve of a whole spectra of different wavelengths. And for each wavelength, we can now take this planet apart into different light compositions, well, like different light lines, and then with material in the atmosphere, it will block more or less light in each different spectral path, and then we get a slightly different spectra for every single wavelength. This is the transmission spectroscopy that we can now do with James Webb. And I just showed you this with like 3 colors, but in reality, the really, really nice thing is that we can do it not just with 3 colors, but with now hundreds, thousands of channels, which is really close to actually having the spectrum of an atmosphere of an exoplanet around another star than the sun. This is one of the first objects that have been like studied to death with James Webb in all the different spectrographs that it has. So these are different spectrographs that you can choose from if you make a proposal for James Webb observations, and you can like see these bumps. It's a bit hard to see, unfortunately. It always goes from basically 0.8 to 10 micron, and these different filters take out different parts of the spectrum in the program, and you can see these bumps. This, for example, would be mostly water features. Here we have a huge CO feature, and then this is the SO2 feature. Unfortunately, the resolution of isn't quite as good for you to see this, but this is basically all these bumps really relate to the species of molecules in the atmosphere. And in the program that we want to do, we are using this filter here. So this is wavelength between 2.5 micrometer to roughly 5 micrometer wavelength, and it's really good in looking at the CO2 feature, and this slope belongs to a water feature as well. So this is coming from the observational side, but we now suddenly have the capability of measuring and for the exoplanets. But I'm more of a theorist. I already said this. So how can this help us to understand the formation and the mechanism to form planets, and specifically hot Jupiters? The problem with hot Jupiters is, so we know that planets, as they form, they migrate through the disk, like this guy here, slowly migrates inwards. And then there are two paths in which it could reach the inner orbit. One would be it just migrates all the way through very quickly and ends up in here, like this, at the end of the disk lifetime, and then it just stays close to the star. The other possibility is it migrates more slowly. It doesn't make all the way through the disk. It stops somewhere in between, maybe even beyond an ice line or so. The disk already dissipates, and now it's stuck in an orbit of, for example, Jupiter. How do we now make a hot Jupiter out of it? Is by having a perturber come by and push it into a close-in orbit, in an eccentric close orbit that then gets circularized tidally. And the specialty between these two scenarios is that in the disk, the planet will always be aligned with the spin axis. So if you imagine this is the star, then it will always spin like this. In the scenario where we had to perturb the planet out of its orbit, it will be strongly misaligned relative to the stellar spin axis. And this is an additional information that we can get out of other already already existing observations, and compile a catalog where we have both scenarios. And this can then inform us on, is this the two mechanisms that happen? And if they happen so, how did it change what the planet formed while it was moving through the disk, either very quickly accreting all the material, or slowly only accreting partial material of the disk? So even further into the observational program, to really have a good sample of planets that we now can sample and understand, to understand the different formation in the inner, complete disk and the outer disk only, is we need to find all the exoplanets for which we know the obliquities already. Then we need to define which planets are actually aligned, which are misaligned. So we will always mark the aligned one as orange and the misaligned one as blue, because the misaligned one formed further out, likely beyond the ice line, making them blue. And then we want to look into giant planets that have a significant atmosphere, that we can really measure and understand what molecule composition is in there. And then there's one more very important thing, is smaller stars have a large convective layer which can tidally realign the planet into the plane of the star. And we need to avoid this. We can avoid this by choosing stars only that are so large that their convective layer is very narrow, that does not tidally realign the planets to the spin axis of the star. So they are beyond the break raft. So we are only interested in these bunch of objects. And you can already see from before, here, in the cold star cases, these planets realigned. In the hot stars, you really see two populations. You see a good chunk of planets that are actually well aligned with the stellar spin axis, but you also see a population here which is roughly at 90 degrees, where the planets are really misaligned relative to the star. And from these now, we pick out the 16 best candidates for which we know the parameters well, and then narrow them down even further to have the 4 best aligned and 4 best misaligned planets that give us the best signal to noise. So these are all the objects that we are looking at. They're also in a narrow temperature range to not make them too different. and 4 misaligned, 4 aligned, and they're all above the Kraft break, which means they will not tightly realign. So what we see in the alignment should be really the primordial alignment that happened during formation. So as going back to now, how did they form? We said they form in the disk, they migrated through here. So to understand what they did while they formed, we need to understand what is in the disk. The disk is composed of different molecules, like mainly hydrogen, like 95% hydrogen, but still there's some extra molecules in there, and there's some icy dust in there. And this icy dust freezes out, like these different molecules freeze out at different points. So for example, when the dark red line, this is the CO gas, and the dashed line, this is all CO. So the line, this is CO ices, and the dashed line is all the CO gas you have in the disk. So as you go in, everything eventually evaporates into gas, and before this, everything is in dust. And if you then compare in the C2O ratio only in the gases, then you have this profile, and then if you do the same only for material in dust, then you get this blue distribution, which is usually very carbon depleted, while the gas has a higher carbon content. Now, in the perfect world where the planet would just suck up everything instantly, this wouldn't matter because it would always like follow the same line, because it just sucks up everything that is everywhere, and that has an equal fraction coming from gas to dust. But planets aren't exactly vacuum cleaners. They don't suck in everything all at once. They actually accrete slowly in complicated processes, step by step. And these change over time, and they change in location, and they change with temperature and everything else. So how does the accretion of a planet actually work? Initially, we will have a small planet core. In our case, we started with something already quite large because we want to end up with a gas giant that is like 300 Earth masses in total. So we start with 5 Earth masses core. And this 5 Earth masses core is embedded deep in the gap, in a disk. It's surrounded by pebbles and gas. So pebbles here in blue, the gas is the red background, and these dots, you see the black ones, this is also, they are planetesimals swirling around as well. Initially, the planet is too small to hold on to the gas, but it can very well accrete all the planetesimals that come within its Hill sphere. And its Hill sphere, nicely, is limited in the middle of, like, within the scale height of the dust that is like swinging around the midplane. So it will actually accrete dust from all sides and very efficiently to grow its core further and further very quickly, just from solid material alone. After that, eventually, it starts to open a bit of a gap, and it can very slowly hold on to some of the gas while it slows down in pebble accretion, because the Hill sphere actually extends even above the midplane. And then eventually the pebble accretion is completely shut off when the gap gets so wide that basically there's a pressure bump forming that keeps off the dust from entering the gap in which the planet now sits. And it only will accrete gas from the accretion stream and start eventually, when the planet has as much gas as it has in solid mass, the atmosphere contracts together, basically like a sink pulling in all the gas all at once, and then starting a very rapid gas accretion phase, the runaway gas accretion phase. And then eventually this slowly shuts off if the planet gets just too large. The gap is so deep that even the gas can't reach the planet anymore. And then we have a truly giant planet that with the Hill sphere that even extends the whole disk. But one thing we have to keep in mind is there are still these planetesimals around, and they can still continue to hit the planet all the time, all the while all of this is happening. And the larger the planet gets, the more efficient this becomes, because it has a larger cross section. In a model, what I just explained, we start here. This is the first bit. This little blip is the core growing from the initial 5 Earth masses very quickly to like 7, 10 Earth masses, just in a very quick rush of accreting a little bit of solid material. But then the solid pebble accretion shuts off at this point already, and we very slowly accrete this little bit of gas that the planet is just able to hold on, until we reach the point where solid and gas is now in equal proportion, and we enter the runaway here. This is now basically between here and there. Enter runaway. Eventually, the planet gets so large, it kind of isolates itself up here, because its healthy is so higher than the disk, and the gap is wider than so wide that the gas can't really get close to the planet anymore. And then we're in this very slow gas accretion phase again. So this is how the planet grows. And meanwhile, while it does all of this, it's moving from the outer disk towards the inner disk. And as it does so, it will accrete some dust material. So this is the dotted points, and some gas material, which will be the dashed line. So initially, we start accreting now these molecules first in dust form while we are in this phase here. And then when we have the rapid gas accretion, we can accrete any gaseous material very quickly and have a larger abundance of this molecule in the gas. And this is how we then can create a complete composition of the atmosphere of our planet. So if we now do this very simply and quickly for our sample planets, we could imagine in a fiducial model, we just set one temperature, we set a simple dust to gas ratio in this model, we set a simple total disk mass and a simple radial speed of all the material, like of the disk inwards. If we set all of this fixed, and we can have a nice fiducial model in which we only change how much planetesimal accretion happens onto the planets, and we get these nice relations out. And we now pick planets that reach the inner disk, and we pick planets that need an extra kick, an extra perturbation to reach the inner disk, and they stop at like beyond 1 AU. So they would be the cool misaligned planets, and then we have the other population of those that migrate all the way in. Those will be the aligned planets. And if we now just randomly choose 2 metallicities that are a likely scenario for planets from other observations that we've done, like metallicity of 3 times solar and 30 times solar, we can actually make a prediction of what would we be able to observe with the James Webb Telescope in measuring the C/O ratio in these observations. And the nice thing is, so depending if we have a high metallicity, then we have 2 very distinct peaks in the C/O ratio, meaning we can really distinguish if our thought scenario of forming these planets by accreting the material of the outer disk and the inner disk is correct as we stated, because we have 2 different peaks that we can then compare with our measurements. However, I already told you this is a nice fiducial model. So basically, for one, this is the observations that we have so far. The last observation was taken in July. So right now we're in a state where from this nice spectra, where you definitely can already see that there are bumps and slopes, we are in a state where we want to retrieve now the actual molecule and molecular abundances and elemental abundances in the atmospheres of these planets. But we do have the data now really to do this, to have a sample from which we then can inform the model and like basically trace back, is the atmosphere corresponding to what we believe is the formation of these planets, and can our formation model explain the planet formation of large giant planets. So I told you that in the fiducial model, we've fixed a whole list of parameters, but there's no good reason to, unfortunately. So in reality, we don't know about a whole lot of different parameters, a whole much. We have ranges of the temperature that would be realistic for, even if we know the stellar temperature, there's still a range of temperatures within the disk that could be realistic. There's a range of pebble sizes that have a different drift velocity that could be realistic. There's a range of disk masses or accretion, disk mass accretion that could be realistic for a disk. The dust to gas ratio is also not a very well-known parameter. And then, of course, the planetesimal fraction that we already played with, we also don't really know how much planetesimals there are in an extrasolar system, because there's not really a good way to measure them at all. So if we play now with all of those, we created about 180,000 single models, varying all of these parameters all at once, and then it gives us this distribution. So the orange ones are those that we consider the aligned planets, because they're close in and they're large enough. And then these ones we consider the misaligned ones. You see a slight change in color. These slight changes in color actually represent different parameters. You can see first off, it's all nicely mixed up, so these parameters don't change this distribution too much. And there's a lot of parameters if you mix all of it all at once. So what does it now look if we go back to where we had this simple line when we have the planetesimals? Just like the more planetesimals we have, the more metal, like basically the oxygen over hydrogen is a measure of the metallicity in the system. And more solids in the form of planetesimals means more metal-rich final atmospheres. But from the line we had before to here, you suddenly figure out this is not as simple at all, because it's not like we have this one nice, neat little track. Instead, we have this whole mess. But actually, within this, we can still find some relations and some logic behind it, and some things that we can later test if we find the planets sitting in its C2O over O to H ratio somewhere in this diagram. So the first behavior that we can see is, like, if we follow this line, everything that is on this side of the line would be formed with very little planetesimal accretion. If it forms with little planetesimal accretion, it will only get solid material very early on in the system. And even if you have a very high dust to gas ratio, like 10% dust relative to the gas, even then you will only ever end up no more than 3 times solar, and you will also have a very high carbon to oxygen ratio relative to the other systems. The second one is if we assume that the gas giant is very much more efficient in its phase accreting the atmosphere, in accreting gases relative to the dust or the planetesimals, then it's these saturated colors all of those saturated colors are systems where it's really quickly accreted gas, much more gas than dust. And in this case, where the gas accretion is dominant, we also find that the C/O ratio will always be quite high, and we cannot exceed the 10% dust to gas ratio that we initially put into the system. So it will always be in this regime. So if we would find all of our planets sitting somewhere up here, it would point us to maybe gas accretion is really important, and dust or planetesimal accretion isn't important for this system at all, and there's no solid material contributing to the accretion of the giant planets in the late phase. And then these different tracks here are different dust to gas ratios. So the higher the dust to gas ratio, the more the whole curve basically shifts to the right, increasing the metallicity while maintaining the same distribution of carbon to oxygen. And then the last point is, if we somehow find systems that have these very high metallicities above 10, then actually we are in a regime where we should see a clear split between those planets that are aligned and those planets that are misaligned. So the ones that are misaligned should have a higher C/O ratio relative to those that are aligned. And if we could observe this, then we would have really also a good indication that this orbital mechanism, shifting them from being aligned with the spin axis relative to being misaligned, is actually the mechanism that leads to these different populations of planets. However, this was already a bit messy. However, there are still more assumptions that we already still put in these models that we need to consider if they have additional effects that might be important for the model still. One of those assumptions is that everything from our 5 Earth mass cores that we accrete later on changes, is mixed perfectly throughout the atmosphere and contributes in the same way to the final atmosphere as everything else. So the first pebble hitting the planet is as well mixed as the last bit of gas cloud that comes into the atmosphere. And we could ask if this kind of completely mixed atmosphere totally makes sense. So this is the same figure as before. Everything is perfectly mixed. However, we can also say if we only consider the final 10% of the whole accretion, then we have only the thin layer of the final 10% of mass coming into the planet really makes up what the atmosphere looks like. And in this case, we see again, the saturated colors are those where the gas accretion dominates, and the pale colors are those where dust accretion dominates in the total contribution to the molecular abundances. And in these cases, you can see that both of them start to separate. Like we have the split that we had before here, but we also have a split in the gas accretion happening here. So in both cases, the aligned planets have a lower C/O, but they are at different rates relative if gas accretion is more important or whether dust accretion is more important. We can make this even more extreme if we only consider the final 1% of all accretion, then you see it even more clearly, and you see the aligned planets go even further down in C/O ratio. And then we can really see these two splits, which could also help us actually. And this was one of the nice parameters that could help us make a better prediction for the planets. Or if we find out that all our observations are up here and then the other ones are all down here, then we would know that actually the atmosphere is not completely perfectly mixed, but it's basically layered, and only the final bit of accretion is really important to determine the composition of a planet. Another thing that we just took for granted is we said that we accrete dust and then that the dust would contribute to our atmosphere. But that doesn't need to be the case, because dust is not just ices, it's also made up of a lot of silicate oxides. These silicate oxides bind a lot of the oxygen that contributes to the atmosphere if we say that it is mixed up into the atmosphere. But what if this silicate, instead of contributing to the atmosphere, forms clouds or just drains out into the core instead? So again, we have our formation models of our planets, the total dust gas content, total dust content, and now we have the gas contribution, the dust contribution, and then these green lines in between is if we exclude the dust from the molecular abundance. So we measure the C2O ratio. If we include that the silicates add more and more oxygen in the final bit of accretion, then these lines, this blue line goes always down. However, if we say the silicate does not add oxygen, the final thing that adds a molecular contribution to the atmosphere is long-chained carbons. This green stuff, this green bump is made up of like basically very long chains, like carbon grains with with long chains, and those may rise then the C2O ratio upwards instead of always sloping down. Now, in our distribution, this is the old one that we already know. What happens is this is what it looks like if we exclude the silicate from contributing its oxygen to the atmosphere of the planet. Now the misaligned planets that formed further out in the disk have less carbon than those that formed like further in the disk. Because now the final bit of a solid material that can help the accretion is this long-chained carbon chains rather than the silicates that would add oxygen instead of carbon. And the whole trend we had before down here where we saw the split switches. So we now go from the aligned ones should actually be more carbon rich than the misaligned ones, if we consider that maybe silicates rain out or are accreted to the core. And in general, because we are missing all this oxygen, the whole line shifts just upwards by two values higher than 0.6 C2O ratio. Now, another thing that we just take for granted is we just say, okay, we have one solar abundance of material that we distribute. Somehow we have like CO gas is one of the main carriers of carbon and oxygen in our system. It's basically everywhere and it's nice and neat. However, there are a lot of people, like a lot of research going into that CO can actually interact on the surface of grains to be reduced and to form ices or to be reduced into other longer chain carbon species. So what if our CO is actually depleted into other species that are carbon and oxygen carriers? If we do this, then we see that the lines wiggle up and down and aren't as clear, but it depends on the exact reaction. So it's not a huge change in the trend. So the gray ones are the models we had before, but it basically shifts if the C2O a little bit up or down, and especially if we take out the C2O gas very early on into an ice, then we can reach much higher C2O ratios, because suddenly the only gas that the planet accretes is methane instead of CO, because the CO is instead bound in ices, and the methane only contributes carbon to the planets. And then suddenly we have also very high carbon to oxygen ratios as well. So it's complicated. And then if we further appreciate the fact that we don't really know how much refractory carbon, so organic grains of carbons we have in the system, the whole trend can shift up or down and stretch. So the pale colors are the original model. And now the dark colors are models where we changed to a third of the carbon grains we initially had. And what this does is it basically stretches the whole model, because suddenly the carbon is accreted from gases rather than from these very late carbon grains. And especially in the case where we don't use the silicates, oxygen, and now we also reduce the amount of carbon grains, the whole model basically merges together, and there is no clear distinction, because in the end, the final bit of accretion neither has oxygen nor a lot of carbon in it anymore. So yeah, the truth is, it's all complicated. It's there should be one more slide. Okay, it's a different, let me just, okay. Wait, just 1 second. Should be one more slide. Anyway. Let me. Otherwise, okay. Okay, the final slide is missing, but basically, if we look at all of this, we have these models, and now we could think, okay, it's very horrible, because now we have this whole zoo of possible predictions depending on what we consider in the model. Already in this one plot, we see 4 different corners of possible predictions, but actually this is the strength of the whole program. And the good thing about it is I don't need to make this model and make the prediction of what reality is. I make a prediction that is actually in the end fed by the observations of these planets that we will observe with James Webb, that actually tell me which of the models make sense and which don't. And with this, we suddenly will move from this is the realm of possibilities to maybe only this is the realm of possibilities, or only this corner is the realm of possibilities. And by this, just from the observations of the atmospheres and by understanding how formation should work, we can narrow down what formation does and what planet atmospheres do as well. So thank you.
Thank you, Anna. Very interesting work and very complex.
Sorry.
Okay, so now we are open for questions, comments. Anybody would like to make a comment or a question? Well, I have one. You talked a lot about the models, but what we can get from the observation? I mean, you have different filters, and then,
yes.
For instance, if you have, can you from the data get information if it is from the upper atmosphere or mixed, or one of the parameters that are very important in your models?
So yeah, this is a good one to start on this question. So we chose, we chose planets for which we have a good estimate of the equilibrium temperature. So they're in a very certain range of equilibrium temperature between like 16,000, like 1600 to at most 2000. Is a bit of already one of the most trickiest planets we have so far. Kelvin. By this, we really wanted to have a sample that is very self-similar in all other aspects except for the orbital parameters. The good thing with this is that we already hoped to rule out most of clouds, because the clouds would only form at temperatures that should be slightly below this. How true this is something for our global climate modelers to figure out. It looks as if the 3D structure of the atmosphere is more important than we anticipated, but basically we already thought about the problem in advance, that we wanted to have an atmosphere that is as clear as possible. This is why we chose these temperatures, but at the same time you can get, if I can just jump back to the intro slide, you can get out a bit of like the depth and how much you measure of the atmosphere from the spectra if you do a lot of measurement. So basically you have the depth in each. The depth corresponds basically to the blockage of light for each wavelength contribution, and then you have how do I say that?
The width.
You can also very carefully see if the width can give you the depth information in these wavelength bands. But then you really have the molecular features that jump here that tell you how much relative to the overall blockage of light you see in a specific feature, and that gives you a ppm of this molecule for the overall atmosphere relative to like the baseline. So this is kind of the idea, but yeah, this is. I'm very happy that I have to only do these simple models of planet formation and not deal with normalizing the light curves and setting them against the stellar light and worrying about all the fun things that the star does meanwhile and as well while you're trying to have planetary measurements, because this is also a very hard job indeed. Like I think we have one object where we have a flare happening while we are in transit, and then you have to cut this bit of the transit out and try to correct for that as well and things like that. Yes.
Yeah, the data have to be very selective and careful.
Yes.
Okay.
So if we go, sorry. If we look at these, so you see now, you see these, every dot here is not a single measure, like it's not the most narrow slit that we could have. It's actually a binning of slits next to each other. And these are already reduced data sets in which we like try to correct for the star, correct for dim darkening of the star and things of the sort, try to cut out things like flares or a mirror tilt that happened in James Webb. And to make sure that the data is really good, we will also not just do a single retrieval, we will always have two different people using different software doing the same thing. So they like, it shouldn't be one line, it should always be two lines in here, but like for not making it too complicated, one person had already their work done and the second one, and I think for half of them we have the second retrieval as well. And now we're really looking into, okay, what do we now can we now say about the abundances? For example, this is our, like, this is very likely the CO feature. This slope indicates the water. And the unfortunate thing though is like, this is unfortunately just a slope. It's not like a bump. And it's very difficult to get a good handle on the water content, which makes especially estimating the oxygen abundance quite tricky. Need more questions?
Okay, thank you. Anybody else? Question or comment? Any from the audience? Okay, well, congratulations for the interesting work. Out of my scope, but very interesting.
Sorry.
Well, you said that you are happy to work on the dynamics.
Oh yeah.
Our group is mainly dynamics, so it's very interesting. And nowadays, I think it's even more important to have this kind of interaction with different fields to get better results.
I think especially like I like the solar, like I think nowadays sometimes the mechanics is a bit overlooked because it gives us additional information that we can really use to constrain things. Without the without the dynamical information, we couldn't make these nice two samples that can tell us something about the process from going from the disk to the planet in different parts of the disk. And it's a very clever way. So, I mean, I think this is often what is missing, is everyone just wants to redo and do another observation of an atmosphere of an exoplanet. But why do you want to do it? You need to have a good idea of what you still gain to learn. How can you with other information? And I think this is why it's important for all of you. This is what I'm going to say very provocatively.
Yes. Well, good.
The beginning when it's not you, if I understand, like how is separated the two paths, like the faster one and the slow one, and align it and disalign it.
Mm-hmm.
What happens between the 30 and 45 degrees?
So that is an excellent dynamic question. I wish so yeah, in the figure I showed, I glossed over the fact that the measurement of the measurement of the stellar spin is a quite tricky thing. So what you do is you measure the blue. You measure you see the blue shift, so the part of the star that rotates towards you, and then you see the red shift, or the part of the star that rotates away from you, and then you have the planet cross either only, like if it was 100% perpendicular, it would only cross the red half, right? Or if it could also only cross the blue side, and you would know it needs to go exactly like this. In reality, or if it's like 35, it would cross somewhere in between, and then you would block a lot of the red light and a tiny bit of the blue light, or the blue shifted stellar spectrum. The matter, however, is we don't exactly know in which direction the star is looking. It doesn't need to spin like this relative to the observer. It could be like shifted like this, and then the planet like basically pointing towards you, and then any planet orbiting in any scenario would always look as if it was aligned. So in this plot, I underemphasized the fact that this seems to be slightly overpopulated because we are not, like, this is not the most careful measurement, and these might be stars that are pointing more towards you, giving you the impression that they would have a lower alignment. And I think I forgot the people, but there are a number of groups working on to like making this measurement better and finding that actually you really neatly get more of a population of stars that are exactly misaligned and those that are more aligned. But we chose, like for our measurements, really, like we just chose those for which we are completely certain, okay, they are super misaligned, and those are aligned. And the in-between could either just be an observational effect that we don't know, or they were misaligned in a different way to what the two possibilities we lay out for this work, at least. Saying either like resonantly interaction with a secondary planet or something of that sort, that is not quite as heavy as the one that would lead to the complete kind of 90 degrees turnover.
Okay. Anybody else? Any other question? No? So let's thank again, Anna.
Thank you.
Thank you.